there's a lot of different ways to actually implement adjacency lists. I've talked about two of them. You could have the vertices labeled 0 to v minus 1, and then this is literally an array. And you have, I guess I should draw, in this picture, ADJ is an array. So you've got A, B, and C. Each one of them is a pointer to a linked list. This one's actually going to be A, C, and we're done. This one is, oh, sorry, that was B. B, who said it had to be alphabetical order? A is pointer to C. C is a pointer to B. Okay, that's explicitly how you might represent it. This might be a hash table instead of an array if you have weirder vertices. You can also do it in a more object-oriented fashion. You could, for every vertex v, you can make the vertices objects, and v.neighbors could store what we're defining over there to be ADJ of v. Okay? This would be the more object-oriented way to do it. I've thought a lot about this, and I like this, and usually when I implement graphs, this is what I do. But it's convenient to have this representation. There's a reason the textbook uses this representation, because if you've already got some vertices lying around and you want to have multiple graphs on those vertices, this lets you do that. So you can define multiple ADJ arrays, one for graph 1, one for graph 2, one for graph 3. But they could all talk about the same vertices. Whereas here, a vertex can only sort of belong to one graph. It can only have one neighbor structure that says what happens. If you're only dealing with one graph, this is probably cleaner. But with multiple graphs, which will happen even in this class, adjacency lists are kind of the way to go. You can also do implicitly represented graphs. Which would be to say ADJ of u is a function. Or v.neighbors is a method of the vertex class. Okay, meaning it's not just stored there explicitly. Whenever you need it, you call this function and it computes what you want. This is useful because it uses less space. You could say this uses 0 space, or maybe v space, one for each vertex. Depends. Maybe you don't even need to explicitly represent all the vertices. You start with some vertex, and given a vertex, somehow you know how to compute, let's say in constant time or linear time or something, the neighbors of that vertex. And then from there, you can keep searching, keep computing neighbors until you find what you want. Maybe you don't have to build the whole graph. You just need to build enough of it till you find your answer, whatever answer you're searching for. You think of a situation where that might be the case? Where implicit representation would be a good idea? Yeah, Rubik's Cubes. You're really good. I never want to build this space. It has a bajillion states, a bajillion vertices. It would take forever. There's more configurations of this cube than there are particles in the known universe.